Do you see the presentation?
Да.
Yes, we do. Perfect. Yes.
Okay, let me speak from my heart in English. Here I will try to highlight some problems in classification of finite subgroups of the Cremona group. What is the Cremona group? Throughout this talk, K will be an algebraically closed field of characteristic 0, and the Cremona group of rank N is a group of birational self-maps of the projective space by n, Pn. It is a very difficult to, this a very complicated group, and one of the possible methods to study it is describing of its finite subgroups and how one can classify its finite subgroups. I follow the strategy which were described in the paper of Dolgachev and Iskovskih, that they classified finite subgroups in the plane Cremona group. So for every finite subgroup G in the Cremona group, one can find a resolution of singularities and indeterminacies X to pi1. The X is a variety with regular action of the group G, and this morphism is a birational G equivariant morphism. Then we can apply G equivariant minimum model program to this variety and get a G Mori fiber space. But then we know that G Mori fiber spaces is in the situation of the plane Cremona group, we have only del Pezzo surfaces, which are well known, and the conic fibrations, while in higher dimensions, we have many possibilities. What is a G Mori fiber space? It is a projective equivariant morphism X to Y, such that singularities of X are terminal and GQ factorial. The push forward of structure sheaf is a structure sheaf. The relative invariant rank of Picard group is equal to 1, and the anticanonical divisor minus kx is F ample. In the three-dimensional case, we have three classes of G Mori fiber spaces. It is Fana threefolds with Picard group of rank 1, equivalent Picard group of rank 1, del Pezzo fibrations, and conic fibrations. I deal with the first case of Fana threefolds with an invariant Picard group of rank 1. But anyway, classifying all possible automorphism finite automorphism groups of all Fana threefolds is too heavy task. So I restricted my attention to birationally rigid varieties. What is G birationally rigid varieties? G Fana threefolds is G birationally rigid if for any equivariant morphism to any G Mori fibration, we have that this fibration is actually isomorphic to original variety. That means that I cannot transform my variety into another Mori fiber space. It is rigid in the space of Mori fibrations. And G Fana threefolds is G birationally super rigid if additionally we have that the group of birational self-maps of X is actually the group of invariant automorphism, equivalent automorphism of X. Why do I consider G birationally rigid varieties? Because rational G birationally rigid varieties give me unique embeddings of groups into the Cremona group. So if one can if one prove that variety X is G-birationally rigid, Y is G-birationally rigid, and Z G-birationally rigid, and they all are rational, so I have three embeddings of my group G into the Cremona group. In this talk, I talk about G-del-Pezzo threefolds. What is G-del-Pezzo threefold? It is a G-fan of threefold such that the anticanonical class is divisible by 2. And it means that this half anticanonical divisor is a del-Pezzo surface. This is a reason why they are called G-del-Pezzo threefolds. And one of the most important invariants of such threefolds is a degree. It is a cube of minus half of kx. It is a natural number from 1 to 8. If it is 8, then actually X is a projective space. And in my talk, I will consider varieties of degree 2. It is a double cover of P2 or of P3, which branched in a quartic. If the degree equals to 8, then all G-birationally rigid del-Pezzo threefolds were classified by Cheltsov and Shramov. They classified all subgroups in PGL4 such that the corresponding G-del-Pezzo threefold is birationally rigid. G-birationally rigid del-Pezzo threefolds of degree 4 and 3, which are intersections of quadrics and cubics, were classified by me earlier. As I said, del-Pezzo threefolds of degree 2 are double covers of P3 ramified in a quartic. And since I interested in subgroups in the Cremona group, the most interesting threefolds are rational threefolds, of course, for me. And there is a theorem of Cheltsov, Przylkowski, and Shramov, which says that non-Q factorial nodal quartic double solid is rational if it has, in all cases except one, if it has exactly 6 nodes and can be obtained from a smooth cubic threefold, which is, of course, irrational. By blowing up a point and connecting 6 lines, which intersects with canonical class upstairs by 0. And in this paper, they gave a conjecture that every Q factorial nodal quartic double solid is irrational. Okay, here is a classification of G-del-Pezzo threefolds of degree 2. And in this table, the most important columns for us is the first, second, and 8th and 9th. The first column is the number of this class in the table. The second column is the rank of the divisor class group. The last column in the number of nodes if all singularities of del-Pezzo threefold are nodes. And the 8th column is the number of planes on del-Pezzo threefold. Okay. Here's several easy constructions which can help us to understand that in some cases, G-del-Pezzo threefold is necessarily non-G-birationally rigid. For example, if there is a G-invariant singular point, then X is G-birational equivalent to a G-conic bundle. It's no more than a projection. A projection from this point gives us a structure of conic bundle, because every line intersects quartic in a node and two other points, and double cover of such a line is a rational curve. Also, if there is a G-invariant line in P3, then X is G-birational equivalent to a G-Mori fiber space with a base of positive dimension. And the third fact tells us that if we have a G orbit of 5 singular points, when G is G-birational equivalent to a G-conic bundle. It is not true if these points are in general position, in fact. But if they are not in general position, then we can find a G-invariant singular point, and in this case, we also have a G-conic bundle, like in the first case. Also, there's a proposition that if we have a G-orbit of 3 nodes, then X is not G-birationally rigid. There are 3 cases. If they are on one line, then we have a G-invariant line, so it is not G-birationally rigid. If they are in general position, but every line through 2 of them are line ramification divisor, then in fact we also have an invariant line, because we can intersect our quartic with a plane. We have 3 lines, and so we have 4 lines which is J invariant. And if lines through 2 or 3 points are not in ramification divisor, that it is a calculation which tells us that that case of link which starts from belonging at these 3 points give us another variety. Also, there is a link with center in 4 singular points. Assume that we have a G orbit of 4 singular points, and they are in general position. So we can assume that they have such a coordinates, and they can consider a self map from weighted projective space P11112, which is given by this equation. Then X is transformed into another, in general situation, quartic double solid. But sometimes it is birational automorphism of X. So in this case, we cannot say that variety necessarily G-birationally non-rigid, but it gives us some conditions on the equation of corresponding double cover. Okay, let us start with quartics with 15 and 16 nodes. They are hyperplane sections of the Igusa quartic, which can be given explicitly by these equations. Igusa quartic is singular along 15 lines, and the intersections with a general hyperplane gives us exactly 15 nodes on the quartic. So general intersection of the Igusa quartic with a hyperplane is a quartic with 15 nodes, and all of them can be obtained in this way. And how can we obtain a quartic with 16 nodes? We must take a hyperplane which tangent to Igusa quartic in 1 point. So we get 1 additional node, and we get a quartic with 16 nodes. Also, there are 10 hyperplanes such that the intersection with the Igusa quartic is a double quadric. And such lines and hyperplanes form a configuration in which every line lies exactly on 4 hyperplanes. Every hyperplane contains exactly 6 lines, and every 2 hyperplanes have exactly 2 common lines. This fact helps us to classify automorphisms of quartic with 15 nodes. And we get the following proposition, where is only one G-birationally rigid Pezzo threefold of degree 2 with 15 nodes. And it can be explicitly given by the double cover of the intersection of the Igusa quartic with hyperplane x equals to 0. And in this case, group G can be S5, A5 times C2, or C5 times C2. In the case of 16 nodes, it is not very convenient way to describe automorphism groups. The more convenient way is to consider such variety as a Kummer surface of the Jacobian or the hyperelliptic curve of genus 2. And from this fact, one can classify all automorphism groups of such surfaces and of del Pezzo threefolds as a consequence. Okay, let us consider the configuration of lines and planes of the quartic with 15 nodes. If we delete from such a configuration one node which corresponds to a node, and all points which corresponds to planes which contain such a node, we obtain a configuration of 14 points and 6 planes. And if we delete 2 points and all planes which contains them, then they obtain a configuration of 13 points and 3 or 4 planes respectively. And there is a proposition that such configurations are exactly configurations of nodes and tangent planes on quartic with 15 or 14 nodes respectively. That means that we know that automorphism of such a quartic restricts to the automorphism of configuration. So in every case, we have a G orbit of nodes, or we have small orbit of nodes. And as a corollary, G del Pezzo threefolds of degree 2 with 15, 14 or 13 nodes are never G-birationally rigid, because in every case we have an orbit of small size of nodes.
Sorry, how on the level of idea do you prove the previous proposition? You just count the parameters, or what? How do you prove the proposition?
I know that I have 14 nodes and 6 planes, 12 divided by 2, because every plane on del Pezzo threefold gives me, every plane or tangent to quadric along conic gives me 2 planes. Mm-hmm. And now I know that every 2 planes intersects in 2 common nodes. Every plane contains exactly 6 of them, and it is a combinatorics, I say, nothing more.
But I just mean, so what does the proposition actually mean? It means that so the configuration of Igusa quartic nodes is not unique only in the combinatorial sense. It's also unique just as a projective configuration, right?
Yes.
Any 2 of them can be sent to each other by projective transformation. Is it true that every 13 node configuration of a Pezzo surface of degree 2 can be sent to each other by projective transformation?
I don't think so.
Well, or at least there are a finite number of such configurations up to projective transformations.
Yes. I mean, it is nothing more than combinatorics. I say I have 6 nodes. I have 4 nodes on other plane. I have
no, I totally understand that you can prove that combinatorially these 14 nodes is a part of the 15 node configuration. But do you also mean that these, say, 14 nodes are contained in the set of nodes of the Iguza quartic?
No, don't say.
Then I really don't understand what does the proposition mean. So such a configuration.
I mean I have a combinatorial structure of nodes and planes.
Mm-hmm.
So I know that some nodes differs from others. They contains in some of them are contained in 4 planes, some in 3 planes, mm-hmm. some in 2 planes maybe. So necessarily I have 2 distinguished nodes which are contained in 2 planes. I can't remember exact statement, but it sounds like that.
I see. So I was just misreading the proposition. Yeah. Great, that's fine.
And if I have 13 points, in fact, I have distinguished 1 node in any case. Okay. In the case of 12, okay, let us consider the case 22. I have 12 or 13 nodes and 8 planes on Del Pezzo threefold, and that means that I have 4 planes which tangent to my quadric in a conic. In this case, I can assume that these planes are coordinate planes. So I have G orbit of at most 4 elements, which are points 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1. And also I know that intersection of my quadric with every plane is a double conic. And from them I, by direct computations, can obtain the following proposition. If such Del Pezzo threefold is G-birationally rigid, then it can be given by this explicit equation. I mean that in other cases, the group out X is too small, and in any case, I can find something invariant line or invariant node maybe. Okay, and this group is C2 squared R times S4 times C2 if this alpha is 0 and C4 times C2 otherwise. Okay, let us consider types 20 and 18. In this case, I have 12 nodes and 1 plane, which tangent to my quartic along a conic. Or I have 11, 10, 9, 8, or 7 nodes and 1 plane and 1 plane. Okay. So I have distinguished plane and a distinguished conic which lies in that plane. Thus, I have the shorter graded sequence 0 to h to automorphisms of y to h prime, such that h is a cyclic group which acts trivially on the plane, and h is a subgroup which is a group in automorphism of my conic. And in fact, I can prove the following, that X has 10 or 12 nodes. I cannot have 11 nodes because in this case, I have triple of nodes. I cannot have 9 nodes or 9, 8, or I cannot have 11, 9, 8, or 7 nodes because in these cases, I will have 1, 2, 3, or 5 nodes in one orbit. So I have that my variety have no chance to be birationally rigid. Also, I know that H prime is isomorphic to A4 or S4 because I have an orbit of length 6, so it cannot be S5 or A5. And if it is smaller than A4 or S4, then I have invariant line in my invariant plane, so it is not G-birationally rigid also. Then I know that H is trivial. It is not obvious, but it follows from some computations. And then I can write down equations of X. In any case, it is a 2, 1, or 3 parameter space of such equations. I write only the simplest case if H prime is S4 and X has 10 nodes. Then I have explicit equations, which is the following form. Okay. All other equations look similarly, but maybe these 2 parameters or okay. Let us consider the Pezzo threefolds of degree 2 of type 16. What does it mean? Type 16 means that I have at most 11 nodes. I have the Picard group of rank 2, and I have no planes. In fact, what does it mean? I have no planes, but I have the following picture. In this case, I have 2 structures of fibration of my del Pezzo threefold over P1. All of them given by one-dimensional pencil of Weyl divisors, and their sum is a canonical class. So in this case, I have a family of quadrics into 3 whose intersections with ramification quartic is a double surface. If I have a family of quadrics, I have suppose I have a family of quadrics which parameterized by a conic in space of quadrics such that every intersection of a member of my pencil with ramification quartic is a double surface. Then I mean that every such quartic is reducible in my del Pezzo threefold. And one member gives me 1 pencil of Weyl divisors, while other give me another pencil of Weyl divisors. This family parameterized by a conic in space of quadrics, so it can be given explicitly by equations p squared q1 plus pq q2 plus q squared q3. The q1, q2, and q3 are free quadrics. Ramification quadric in this case is a discriminant of such an equation, simply. And since all singularities are nodes, I have the following proposition. Free quadrics given by Q1, Q2, and Q3 intersect transversally in 8 points. Also, I know that X has exactly 8 nodes, because otherwise I will have an orbit of length 1, 2, or 3, and it is impossible. I have the short exact sequence: 0 goes to H, goes to automorphism group of Y, goes to H prime. The H preserves every quadric in my family, and H acts on P1, which parameterizes my quadrics. Also, I know that I have exactly 8 singular quadrics in my family. There are no more than 8 because I have determinant is a polynomial of degree 8. But if all my singularities are nodes, I have exactly 8 single quadrics, and all of them are cones with zero-dimensional vertex. From this fact, and also the vertices of these cones are in general enough position, so I have that H is a trivial group. Also, by direct computations, I show that H prime cannot have an element of degree 3. So H prime cannot be isomorphic to A4, S4, or A5. So H prime is quite small group. It is cyclically or dihedral. So in this case, my variety is not G-birationally rigid. Okay, let us consider type 19. In this case, X has no planes, has 12 nodes, and Picard group, and divisor-colored group is of rank 3. In this case, we have the following theorem by Yuri Prokhorov that tell us that in this case, I have let Fi be the set of all complete one-dimensional linear systems of failed devices without fixed components. That every Fi defines a fibration of such Q factorization of X over P1. Every fibration factors through a P1 fibration, and they have exactly 6 such linear systems, and they form the following diagram. In this diagram, 2 vertices are connected by line if the corresponding fibrations over P1 factors through the same P1 fibrations. I have 6 linear systems, one of them F1, one F2, one 2s minus F1. S is a half anti-canonical divisor. That means that this 2s minus F1 is minus kx minus F1. Here is misprint. We have minus kx minus F2 and S minus F1 plus F2 and S plus F1 minus F2. These divisors give us 6 systems, 6 linear systems. From this fact, we see that we have the short exact sequence. 0 goes to H, goes to automorphisms of X, goes to H prime, where H preserves all pencils, preserves F1, F2, etc. And H1 permutes pencils, so it is a subgroup of D12. Let G be a subgroup of out X, which preserves the pair of pencils F1 and minus Kx minus F1. It is a subgroup of index at most 1 or it's a group of index 1 or 3 in automorphism group. So it is big enough to understand the whole geometry of X. And J is an automorphism group of a pencil of quadrics p squared q1 pq plus pq q2 plus q squared q3. It is the same construction as in the case 16. And I have the following proposition. All quadrics corresponding to QIs intersect transversally in 8 points. I have exactly 4 singular members in my pencil, and all of them are cones and with 0-dimensional vertices. And their vertices are in general position. And also, if Q1 corresponds to a singular member, then Q2 contains the vertex of Q1. In this case, this vertex will be the node of the quartic. Also, we have the short sequence 0 goes to G prime, goes to G, goes to G prime prime to 0. The G preserves all quadrics in my pencil, and it is in fact isomorphic to C2 in the power of I, the I from 0 to 3. And H prime is a subgroup of automorphisms of P1, which has invariant set of 4 points. And in fact, I can explicitly write down equations of Q1, Q2, and Q3 and do some quite long computations and obtain that in almost all cases, I necessarily have invariant objects which give me transform into another G modifiable space, except one case. If G is birationally rigid, when I can explicitly write down equations of Q1, Q2, and Q3, and the group out X is S4 times C2 squared in general situation, and if alpha is equal to 0, then my group little bigger. Okay. Also, I can easily see that all nodal del Pezzo threefolds of types 17 and 21 are not G-birationally rigid. Let us see it. In the case 21, I have exactly 4 planes, or equivalently, I have 2 planes in the space which tangent to my quartic, and so I have an invariant line. And in the case 17, I have exactly 11 nodes. All of them form one G orbit. So I have an automorphism of degree 11. I can describe all such automorphisms, all possible quartics. And I, by direct computation, see that none of them is a quartic with 11 nodes. Or except several cases, but in these cases, I have something like twisted cubic through all of them. So I necessarily have invariant twisted cubic. So the automorphism group is a subgroup of automorphism of P1, and it has an orbit of length 11. So it is cyclic or dihedral group. So my variety is never G-birationally rigid. So in previous slides,
can you go to to page 20 of your presentation? Yeah, so you have a proposition, and do you have a converse statement? You say that if X is G-birationally rigid, then something. And do you mean that if Q1, Q3, and Q2 are like this, then X
it will be later.
Sorry?
A bit later, I will tell something about birational rigidity of such things.
Okay, but because I was surprised by the next page where you say that the classification is already done.
I classified not birationally rigid, I classified all candidates to be birationally rigid.
So you have a list which is possibly too large, right? But you know,
not too large. It is something like 10 possibilities, and all of them are either concrete variety, either it is a one-dimensional family.
but I mean that some of these varieties may still be not birationally rigid.
Maybe.
Uh-huh.
Okay. In Q factorial case, the situation is much more complicated because the geometry of my Del Pezzo threefold is too weak. It has no invariant pencil of quadrics. It has no invariant planes a priori. So the only way to describe situation, describe candidates to be birationally rigid, it is direct computation of varieties which have big group of automorphism. But something I can tell, there are no nodal G-birationally rigid Del Pezzo threefolds with 9 nodes, non-Q factorial and Q factorial case. The only one threefold with 7 nodes can potentially be G-birationally rigid. It has the following equation, and its automorphism group is at least semi-direct product of C7 and C3 times C2. Maybe it's bigger, but I don't know the full automorphism group. And in the cases of 8 and 10 nodes, situation is much more complicated. I have quite big list of possible candidates, but in most cases, I even don't know the whole automorphism group. But in the case of 10 nodes, I can say that I have 2 orbits of nodes, one of them of 6 elements and one of 4. And I have that the automorphism group of X is C4 times C2, or maybe C4 times C2 squared. And the case of 8 singular points is still is much more complicated because I can have 2 orbits of length 4, and in this case, computations are quite hard. They are not hard, but there are a lot of them, so I cannot write down the concrete proposition in this case.
I'm sorry, and what? So your orbit of length 4 is in general position.
If 10 nodes, yes, they are in general position. If
but then you have a link. Then you have a link starting from these points, right?
No, sometimes it leads me to original variety.
Okay, and on this you don't have any control, or do you?
Sorry?
Do you have any efficient way to check if the variety is the same or different?
Of course, I have explicit equations. I can write down the equation of original variety and second variety, and can.
But then, in this case, why do such orbits cause any problems to you? If you say that you know the link and that
it is in situation of 10 nodes. In situation of 8 nodes, such links give me many equations which are how to say, in the case of 8 nodes, I have many possible automorphism group. I have many possible ways how they act on two quadruples of singular points. I have many possible variants how such quadruples can okay.
Well, I see the situation may be more complicated. So an obvious way out is to change the question and consider solid varieties
That's
instead
why
of rigid.
I hope that someone will prove that all Q factorial nodal threefolds are irrational.
All Q factorial nodal threefolds are irrational.
Yes, it is your conjecture.
Yeah, but it's I would say that it may be hard.
Okay, but I hope that it is true and someone give it to me.
Mm-hmm.
Then all of these computations will be almost in vain.
But the previous ones from the previous slides, there will be not, because
yes, because all of them are rational.
Mm-hmm.
Okay, what will I do with G-birational varieties? For checking G-birational rigidity, I need to consider G-invariant linear subsystems M in minus mu kx for different mu, and all of them must be without fixed components. And for every M, I need to find all center of non-canonical singularities. If there are none of them, then situation is very good. Then my variety is birationally super rigid. But sometimes some non-canonical centers can appear, and in this case, we need to check Sarkisov links, which starts from these non-canonical centers. Sometimes the Sarkisov link fails on the first step. For example, if I obtain elliptic fibration, it is a Sarkisov link which lead me to a non-Mori fiber space. So in this case, the situation is good, but sometimes the situation is much more complicated. Okay. And if all Sarkisov links are birational automorphisms of X, then X is birationally rigid. There are three theorems by different authors which tells me how to deal with possible non-canonical centers. If I consider smooth point as a non-canonical center, that I have that multiplicity of the intersection of two general members of my linear system in this point is at least 4 times mu squared. If I have an ordinary double point as a center of non-canonical singularity, then multiplication of divisor D in this point is at least 1. And is the curve C is an irreducible curve such that it is a center of non-canonical singularity, then the multiplicity of this linear system along C is greater than mu. How can I use these facts? The first fact I use in the following way. I know that the G orbit is big enough. Then I have multiplicity of Z in many points is at least 4 times mu squared. And if I intersect this Z with an appropriate divisor, then I sometimes obtain that the intersection number of Z with such a divisor is big enough. Then I cannot have multiplicity 4 times mu squared in this point, and then such a point is not a center of non-canonical singularity. If I have multiplicity of divisor at node at least one, I can consider some curve with good properties, and sometimes I can intersect this curve with my divisor and get the contradiction. And in the case then C is a curve, then such a term give me bound for degree of my curve. So I have to find all curves of small degree which are invariant with respect to my group. And sometimes all of them, in fact, sometimes I prove that there are no such curves. Okay, as we see before, we have many potentially birationally rigid varieties, and the group C4 appears in our classification very many times. So it is natural to check then the variety is S4 birationally rigid. And I have the following position. S4 del Pezzo threefold is 16 nodes is not S4 birationally rigid because it has orbit of length 1, 3, and 20. I have invariant nodes, so the variety is not G-birationally rigid. Varieties with 12 nodes of types 22 and 19 are S4 birationally rigid if they are S4 Q factorial. It means that if my invariant class group is of rank 1 with respect to the group C4, then my varieties are S4 birationally rigid. In fact, all smooth points are excluded by the first theorem, all double points excluded by second theorem, and all potential curves are excluded by the third theorem. Except one case, then I have invariant set of two smooth points, but the link which starts from them leads me to elliptic vibration. Okay, in the cases of types 12 and 18, I have almost the same, but there is a S4 invariant rational curve of degree 6, which lies in the ramification divisor. And it is the only possible center of non-canonical this is the only possible non-canonical center, and I think I almost know that it is also impossible, but some difficulties are still stay for me. Okay, I think that's all. Thank you for your attention.
Thank you. Any questions to Artem?
So you consider only singularities, only ordinary double points. What happens if you consider other types of terminal singularities?
Yes, I did not consider other singularities still for many reasons. One of them is that I don't know the rationality of such varieties. And I think it is only a reason. I think, in fact, classification
rationality is rationality, rigidity is rigidity. So it's somehow.
Yeah, but there are many rigid varieties, but if they are also rational, then they have some relation to more simple and more basic things. So it's always nice to know that somebody is rational. But maybe like another form of this question is like do the methods apply to non-nodal varieties?
Some of them, of course, applicable, but for example,
for instance, if your point is not a node, if you have 4 points which are not nodes, can you still perform a link which starts from 4 points?
yes.
So it goes for arbitrary points on the replication divisor, right?
Okay. If I have 4 points in general position, that I know that my equation has no members like x in the power of 4 or x in the power of 3 times y. If my quadratic is singular in 4 points, which is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and 0, 0, 0, 1, then I have that equation of my quartic has no zero coefficients, has many zero coefficients. And in this case, such a transformation always exists, and it leads me to another quartic double solid. And I think the singularities should be almost the same as in X, but I'm not sure. I mean, if I have only members like x squared times y squared or x squared times y times z, then if I change my variables by this monoms, then I will be able to divide my whole equation by x, y, z2 squared. And it leads me to another quartic double solid. So this transformation is valid in any situation, of course.
Okay. Any other questions?
Question about just formulation of the result. Your branch surface is K3 surface.
Yes.
Possibly there is reasonable reformulation. You can reformulate your result in terms of K3 lattices. Did you try it?
I need linear transformations of my quartic because I need quantum field of the Pezzo threefold. While when I consider my quartic as a K3 surface, it knows nothing about the embedding into P3. So if
it means that you just in the lattice you have to fix sample class. Why not? And minus 2 classes as well, the singularities. Possibly it's I don't know. It's maybe it's it can be done, and this somehow simplify formulation and at least unify them. I don't know.
Maybe, but in non-Q factorial case, I have quite rich geometry of my variety. I have tangent quadrics, tangent planes, and it gives me many restrictions of possible groups. So I don't think that in non-Q factorial case it is very reasonable. While is in Q factorial case maybe.
Okay, I see. It's just a stupid question. I don't know. Thanks.
Other questions? Let me also ask one more question. So, what's your feeling about the Pezzo threefolds of degree 1?
I think that there is a conjecture by which I see in Cheltsov's paper that they are birationally rigid when their corresponding automorphism group has no fixed points on P2. And in my opinion, this conjecture should be true. And in the previous, the previous year, I tried to deal with this conjecture, and it seems that in the cases of quite big groups, it's really true. Maybe this conjecture really holds.
I see. So, final call for the questions. If not, let's thank Artem again